So with centripetal acceleration, and again, we sometimes call that radial acceleration simply because it's on the radius. It always points in towards the center of a circle. According to Newton's second law, an acceleration is always the result of some sort of net force acting on an object. And that is still going to be true. An object that is experiencing a centripetal acceleration because it is moving in a circle, that acceleration will be due to the net force acting on the object. So just to talk about a couple examples, as we're driving on the road and we need to take a turn. So the road turns, the car's driving along, but it is turning. Because there is a curvature to this road, we can imagine this has some sort of portion of a circle. Because there's a curvature there, as the car turns, its velocity is changing because the direction is changing. Therefore, there is an acceleration. If you remember, just average acceleration being a change in velocity in some period of time, if we think about an initial velocity right here, and then its next velocity is right here, a v final minus a v initial gives us a delta v that points inwards. The direction of the delta v is the direction of the acceleration. This is why we always get this centripetal acceleration pointing towards the center of the circle. So if we want to think about the net force, so we have this centripetal acceleration the car is experiencing, and that centripetal acceleration points inwards towards this center throughout the whole curvature. In terms of forces, we have the force of static friction between the tires and the road that is not allowing the car to slide outwards. In this particular example, I'm assuming a perfectly horizontal road here. The force of static friction is what we would call the centripetal force causing this acceleration. So to talk about a centripetal force doesn't mean there's just this somehow new force. It's forces we know that we're familiar with, but it is the force that is requiring and causing the object to move in a circle. Now, if we're driving down the road and we are the ones that are going to make the car turn, we know that we turn the steering wheel. So inside the car, we would turn the steering wheel, which of course directs the wheels in a different direction. But turning the steering wheel will not guarantee we go in a circle. If you've ever been driving in snowy, icy conditions, you may have experienced turning the steering wheel, yet continuing to travel straight. So it's not the steering wheel that's making the car go in a circle. The steering wheel is causing the tires to turn, but it's the interaction between the tires and the road. As long as that static friction force is big enough to not allow you to slide off the road, then you will travel in a circle. So we could say in this case that the static friction force would equal the mass of the car times the centripetal acceleration it has at any moment as it rounds the corner. In the y direction, y direction implying mg is straight down to the center of the earth and normal force upwards, we would find that the normal force is equal to mg in this case, assuming this horizontal road. So we could plug in, that goes back. Remember when we say the force of static friction is the coefficient times the normal force? This would represent the maximum possible static friction force. But again, the static friction force can be any value up until reaching that value. So if we come back to Newton's second law, we can substitute in here v squared over r. And this shows us that the static friction force needs to be directly related to how fast we are driving and inversely related to the radius of the curve. Meaning the bigger the radius of curve, the smaller the friction force needs to be. It's easier to go around a turn with a really big radius as opposed to the small radii. If we wanted to equate what Newton's second law is telling us, this is according to Newton's second law, if we wanted to relate that to this maximum, the mass actually ends up canceling. We could solve for a speed here. This would be the maximum speed to not slide off the road. And again, maximum because this force of friction, when we say that's mu s times n, that is the biggest it can be. So there is a maximum speed at which we can travel and not slide off the road. Now, another thing comes into play, and that's rolling the car, actually tipping over. That's a different concept. So that's not something we're considering right now. We're looking only at the sliding off the road. Another example, you may have seen a pendulum before. We call this a simple pendulum. If I have a mass on the end of a string, I pull it to the side and let go, I know it's going to swing back and forth. At any given moment, it could be anywhere. Even though this is not a full circle, the path the pendulum takes is a portion of a circle. And so this mass at the end of the string will have a centripetal acceleration at any given moment in time. And I didn't mean to draw those different lengths. They will change because the speed of the mass is changing. The mass would be traveling fastest at the bottom, so that's when the centripetal acceleration would be biggest. But at any given moment, that centripetal acceleration will be pointing towards the center. At any of these moments, we could also draw a free body diagram where we have tension and mg. That angle for the tension is changing at any given moment. when we say that this centripetal acceleration is due to a net force, we mean forces along this radius line. And so we have to add up. The tension is always along that radius line pointing inwards. Depending upon which moment in time we're talking about, the gravity force is going to have a component as well. So to look at problems dealing with centripetal acceleration, we will need to look at a specific moment in time to relate the forces to the centripetal acceleration. The centripetal forces in this case, though, the tension is always towards the center and a component of gravity. If we were talking at the moment the ball was exactly at the bottom, we would have the tension force upwards, the force of gravity downwards. So when we talk about the net force in that radial direction, meaning towards the center, we would end up with tension minus mg. Those two forces at that moment in time are along that radius line. So these together would have to equal the mass times that centripetal acceleration. So tension is not a new force to us. Force of gravity is not new. But they are considered centripetal forces simply because they are working together to cause this circular motion to happen. Common, if you've ever heard of swinging a pail of water. So a bucket, you have water in here, you're holding it. So here's your shoulder, the dot, you're holding on to it. If you get it swinging fast enough, you can technically get that bucket of water above your head and not have the water spill on your head. If we think about the water, at the top there, the water has a normal force. But again, because it's in the bucket, the surface of the bucket is at the bottom, below it, which happens to be on the top in the picture. Force of gravity straight downwards. There's the centripetal acceleration, simply because it's moving in a circle. At that top moment, that centripetal acceleration points downwards. So we would call downwards the positive direction. The normal force and the force of gravity are both downwards. So this would be the net force in the radial direction. So this would equal mass times that centripetal acceleration. Now this, just at this moment in time, if we imagine just picking up a bucket and holding it up there without motion, we know we're dumping water on our head. It's the motion that we have to have. This bucket needs to be swinging fast enough in order to not get wet. If you remember Newton's first law, any object in motion is going to continue in motion with a constant velocity unless acted on by an outside force. So the water in this bucket is attempting to continue moving in a straight line. So as it was coming up here, it was trying to move in that straight line. Now it's trying to move in this straight line. But the bucket, the walls of the bucket are in the way. It does require a specific minimum speed to not get wet. If we wanted to look at something like that, we could relate our forces to the centripetal acceleration written in terms of v squared over r. As v changes, as the speed changes, it's the normal force that's changing. Right? The mass of the water, assuming we have the same amount of water in there the whole time, the mass of the water is not changing. G is not changing. The radius is however long our arm is, so from our shoulder out to the bucket. So as V changes, the normal force changes. So minimum speed, as we make V smaller, the normal force is going to get smaller. Hopefully just looking at this equation allows you to see that. The minimum speed to not get wet is the speed at which the normal force just barely goes to zero. The minimum speed will depend upon the radius, how far from your shoulder out to that water, the radius of the circle the water is moving through. So that's the absolute slowest, and the water will just barely stay in the bucket. Twirling the bucket any faster than that will definitely keep the water in the bucket, and you will feel the pull of the water, or the push, I guess, of the water against the bottom of the bucket. So we're going to go through a number of conceptual examples as well as problem examples in terms of setting up the problems and solving them. So look for that next.